Reviewing what we covered yesterday. The first thing we covered was the zero factor property, stating that the product of a real number is zero if and only if at least one of your factors is zero. Does not matter which one. You could also have multiples, but if at least one of them is a zero, then the entire thing is going to be equal because you're multiplying by a zero. The second thing we discussed was problem solving. The first thing you want to do is make sure you read the problem, try to gain understanding, the basic concept of it. You may have to read it more than one time. Then we're going to develop a mathematical model of the problem. It could include taking a guess, working out using the numbers in our guess, and then figuring out what the equation is based off of that. And then, of course, we're going to solve the mathematical equation. And then always check your answer, particularly when they're real life problems. You want to make sure that the context is taken properly and that you're rounding and making sure that your restraints are appropriate as well. We also discussed graphing calculators and the limitations that they have. Graphing failure is when you have a graph on your calculator that does not represent the problem accurately because of its limitations, and then also the hidden behavior. Usually that occurs because our window is not appropriate in its size in order to see everything that may need to be seen. So that brings us to today's discussion, which is dealing with functions and also the notation of function. A function is a relationship between an input value that we often call domain and an output value known as the range. Functional notation is usually written in the form of f of x is equal to some equation after that, where the f of x portion could also be equal to simply what we call y. To be a function, each element of the domain should have one and only one outcome in the range. So if I plug in a 5 for my x, I should get a single value for my y, not two. Now, throughout the process of plugging in values of x, I could have y's, the same value of y, show up several times. For instance, I could have plug in a 2 for x, I get a 5 for y. I could plug in a 3 for x and also get a 5 for y. That is okay. What cannot happen is I plug in a value of 2 for x and I get two possible values for y, such as 5 and 8. I need only one particular value for every single domain that I plug in. Take a look at this example of y is equal to x squared. Is y a function of x? And the answer to that is yes. So for each value of x, you only have one value of y that's represented. If we were to graph it, it would have the parabolic shape that we are familiar with from Algebra 2. Because each input in our domain gives us one and only one output in our range, that means when it is graphed, it should pass what we call the vertical line test. The vertical line test of functions states that if I draw a vertical line anywhere on my graph of my function, it should only cross my graph of my line or my function at one point, never two, at most 1 point. So based off of that, if we take a look at these three functions, is this first one a function? Well, if we were to draw a vertical line anywhere along this particular graph, we would only hit the graph in 1 point. So yes, this first graph would be a function. If we look at the second, if we were to draw a vertical line anywhere along this second graph, we would only cross it at 1 point. So it is also a function. And then for this third graph, if we were to draw a vertical line anywhere along this portion here, eventually we would hit a point at which it crosses multiple values. And so this one here is not a function. Change in tandem. sounds really fancy, but a change in tandem simply indicates that there is a change in our output whenever we change our input. So as we change x, y is also going to change. So let's just say that Emma were to earn $18 an hour working a job. If she were to work 2 more hours this week than what she did last week, what would be the change in her paycheck at the end of the week? As we think about this problem, she makes $18 an hour, so her change in pay would be equal to 18 times the change in the number of hours that she works. In this particular case, we say that she worked 2 additional hours. So if I plug in a 2 for my change in the number of hours, I get a value of 36. So she would have an increase of pay of $36 this week as opposed to last week. So that brings us to the concept of domain and range, which we've already discussed several times, even in this lesson. The domain is the value of inputs that you can put into a function, the possible ones. But there is some indication that we need to make sure that what we have in our domain and range, in our function, is going to work out. If merely given an equation, we can use what is called the implied domain, which will be all real numbers that work for that particular equation or that particular function. Now, if you have part of your domain value, like x, in the denominator, we need to understand that you cannot divide by 0. So I cannot have 0 in my denominator. At the same point, if I have a square root or a fourth root, any even root, I cannot take an even root of a negative value. So what's inside that radical, if it has an index that's even, needs to be a non-negative number, 0 or higher. So based off of those pieces of information, we are going to be able to determine the domain of most of our values. Now, also, if we have a word problem, we need to make sure that our domain is relevant. That means if I have an equation, for instance, that's giving me the volume or the area of something, and it's based on side lengths, I cannot have a negative length. I cannot have a negative volume. I cannot earn a negative number of dollars. So in real life situations, you might have additional constraints that you don't necessarily get when you're just given the equation. So that is the difference between implied domain, based on the equation solely, and relevant domain, which is going to take into account all the other pieces that may be part of that problem that aren't necessarily stated. So what is the domain of the square root of x plus 3? Well, I cannot have a negative value inside my radical because it's an even root. So what I'm going to do is I'm going to set my radical equal to 0 and solve for what's inside. So square both sides, and then I have x plus 3 is greater than or equal to 0. If I subtract 3 from both sides, then I get x has got to be greater than or equal to negative 3. If I do that, then all of my other numbers, every value of x greater than or equal to 3, will work out in this particular equation. If we were to graph it, it would look something like this. So take a moment and try to work this one out. What is the domain of g of x equal to the square root of x over x minus 5? So since we cannot take the square root of a negative number, I have to first of all set x being greater than or equal to 0. It can't be negative. At the same point, I also have an x in my denominator. So I cannot have a 0 in my denominator. So I'm going to set the x minus 5, my entire denominator, equal to 0 and solve. When I do that, I end up getting x cannot be equal to the value of 5. And so I now have two portions to my domain. X has got to be greater than 0, but cannot be equal to 5. So when I write this out, I need to make sure that I indicate as such. So therefore, the domain is starting at 0, can include 0, so I'm going to use a bracket, an open bracket, can go all the way to the value of 5, but does not include the value of 5. So I'm going to use an in parentheses for that. It can also include going from 5, but not including 5, so again, an open parentheses, all the way out to infinity. Now, whenever we use infinity or negative infinity, we're going to use a parentheses because infinity goes on indefinitely. It's not in one particular value. It continues on. So we always use an open or closed parentheses when we're dealing with the infinity signs. Now, this middle sign here, that U, stands for union. It's like an and statement. So I've got this as part of my domain and this is part of my domain. What isn't included are negative values and the value of 5 itself. If we were to graph this, this is the way it would look. You'll notice that where x is equal to 5, I will have a vertical asymptote. So it can get close to that value, but will never actually touch it. Try this one. We want to find the domain of a of s is equal to the square root of 3 over 4 times s squared. Now, it also gave some information where A is the area of an equilateral triangle with a side length of S. So my implied domain would be all real numbers from negative infinity all the way to positive infinity if all I had was the equation. However, I have more information than just the equation. Along with that equation, I have some information about what these letters represent. It's area dealing with side length. I cannot have a negative side length. So I have a relevant domain that is more limiting. My relevant domain starts at 0. I can't have a side length of 0, which means it wouldn't be there. If I had a side length of 0, my area would be 0. I can have an area of 0. So it starts at 0 and includes 0, so we use an open bracket, and can go all the way to infinity. I cannot have a negative length. When we graph it, your graphing calculator is going to look something like this. We have the regular parabola shape. However, you need to understand that in this particular case, negatives are not possible. So really, it should just be that right-hand side of the graph if we were to graph this on a piece of paper. Range is the possible values of the output in our function. Range is a lot more difficult to figure out what your possible values are and are not. One of the easiest ways is to graph the function. If we graph the function, such as this one here, 2 over x, we start to see a little bit more easily where y values cannot be. Looks like the negatives are good all right through here. Looks like the positives are good all right through here. But this 0 mark seems to be a problem. Is it capable that this function could be a 0 as my y? I do know that I can't have a 0 as my x value. So you'll notice that here we have a vertical asymptote. But what about the y? Is there a horizontal asymptote at 0? We could check this by plugging in a 0 for my f of x and solving, which we'll do here in a moment. If it is true that 0 is not part of my range, then my range would go all the way from negative infinity, notice the open parentheses, negative infinity to 0, and then pick up at 0 again and go to positive infinity. It would not include the value of 0 itself. So plugging in a 0 for my f of x, solving by multiplying both sides by my denominator to get rid of my fractions, that gives me 0 is equal to 2. 0 is not equal to 2, that's a false statement. So that tells me that 0 does not work for a value of y in this particular function. So 0 is not part of my range. So that brings us to the concept of increasing and decreasing intervals in functions. Here are several examples. This one is a constantly increasing function. As you go from left to right, it is going up. Over here, I have a decreasing function. As you go from left to right, it goes down. This third graph is what we call a constant. So it is not changing as you go from left to right. And then this fourth one, it starts to come down, then it levels off, and then it starts increasing as you move on. So a function is increasing if during the interval that you're checking, every value as you go along that interval, as you increase your value of x, your y values also increase. It doesn't have to be an increase by much, but it does need to be an increase. That is what we consider an increasing interval. If it's decreasing, then that means during that interval, as you increase your x value, your value of your domain, your y value or your range goes down. It decreases. And if it's constant, then that means your change is 0. As you continue on changing your x values, going up in x values, if your y value stays the same, that is considered to be constant. So in this function, where would it be an increasing or a decreasing portion of our function? We are going to begin by graphing the equation. So here on the board is the graph. If we are looking at the portion that is increasing, it appears as though at -2 we have our vertex. So at -2 all the way out to positive infinity, it is increasing. -2 could be included, could not be included. Some books will put a bracket, some books will put a parentheses. So I'm not going to make a big deal about that. Your particular book uses the bracket, so we will use that as well. But -2 all the way to positive infinity is where it's increasing. Where is it decreasing? Well, it's decreasing from -2 backward. So from negative infinity up to -2, it is decreasing. Notice once again that both of the infinities have the parentheses portion because it does not include it, so to speak. And so it is decreasing from negative infinity up to -2. Let's try g of x if it is equal to x squared over x squared minus 1. Again, if we begin by graphing it, go ahead and take a moment and graph this particular function on your calculator. When you graph it, you should have something that looks like this. Now, if you don't see part of this, you want to zoom out a little bit so you can see all three parts of this graph. It does appear as though we have two vertical asymptotes. If we were to take this function and make it x squared over, and I were to factor my denominator of x squared minus 1, perfect square, negative sign in the middle, that means I can factor it into two binomials, x plus 1, x minus 1. So I have two vertical asymptotes because x cannot be equal to a -1 or a +1. So on our graph we have those vertical asymptotes. We're looking at where is it increasing and where is it decreasing. Well, as I go from negative infinity all the way over, I am increasing all the way up until I get close to -1. So I have an increase from negative infinity all the way to -1. Then I go to this graph, this portion of my graph. Well, where is it increasing or decreasing? Well, if I start at -1, it is increasing as I get closer and closer to 0. Once I hit 0, I'm no longer increasing. Now I'm decreasing. So I have two portions that are increasing. It's increasing from negative infinity to -1, and then from -1 to 0. And again, we included the 0 in this particular case. Now, where is it decreasing? Well, if we continue on, it starts up at 0 and decreases the rest of the way until we get to positive 1, but not including positive 1. Once we get close to positive 1, it's going to jump all the way up high on our graph and start decreasing from way up in the upper regions. So my decreasing portion of my graph goes from 0 to 1 and then picks up at 1 and goes on to positive infinity. So we've learned several things today about domain, range, our change in tandem, increasing and decreasing functions. Most of it we have covered at some point throughout the last couple of years, and so hopefully a lot of this was review for you.